Okay, cut-based clustering or divisive clustering, also split-based, many names. In literature you may find out this concept of cut-based methods, but it can be also a little bit confusing that what it actually meant by cut-based. So let me first cover a little bit what is a cut or cut-based clustering. You can find methods like normalized cut and similar, but the point is that these methods a little bit confusingly combine different graph theory and the cost function that they optimize with the algorithm that the cut actually implies. So cut is something that you divide into multiple parts and so on. So this is the algorithm point of view what I try to talk. But then when you talk about graph theory, so the approach is typically that we have the data, and from the data we try to construct graph, and then from the graph we start to cut the links and so on. So sounds nice idea, but let's see, does it really make so much sense? Okay, so these are the questions I want to answer. So what is cut and what it has to do with graph theory, and finally, is it efficient? Okay. So a little bit back to the roots. So clustering method. So what we use. So I use this term of method to define the problem. So have some post function, objective function that we either minimize or maximize, and then clustering algorithm as a way to solve this problem, to find out the optimal solution or optimize it as well as we can. So typically we define the cost function as coolness of one cluster. So if we know how compact or whatever the criterion, based on similarity, based on distance. And then comes the cost function. There's a global or local. And this kind of cut-based methods, oftentimes they don't actually optimize some global cost function itself, but they try to make this cut, separate the graph into two halves or whatever division. Try to make that step based on some criteria. So I would say it's kind of a local optimizer. And yeah, okay, so if we have global optimizer and then we apply some local optimizers, okay, it's kind of a greedy way to optimize it, but if we understand that they may be related. Otherwise, if we just optimize some local cost function, we may not necessarily know what we are optimizing globally. Okay. So many graph-based methods, they assume that there's a graph, and the concept of cut is based on these graph links. There are a couple of links here mentioned, so you may look. So there are max k cut, m cut, ratio cut, and similar methods. So okay, first, so if we have data, we have these data points in somewhere, some data space or whatever form the data has. But to get the graph, how do we get the graph at the first place? So this is where the yes, if we have a graph, if our data is a graph like social networks, then it's a different question. And then we are really onto clustering the graph itself. So graph clustering, in that point of view, it's a completely different goal. But if we want to cluster just some normal numerical, categorical or whatever data, we just have the data and the attributes. So how we get the graph? Well, usually it happens that people just take the normal attributes, calculate the pairwise distances, and then we get the graph. So it's a basically distance graph. If we have n data points, we have n power 2 distances, and that's a graph. So it becomes as a complete graph. Okay, nice. So we have a way to get the graph, and then we can apply basically graph-based methods. But yes, so it's a complete graph, and then again, from a complete graph, okay, first is what we have. If we have the data points, we have 2 data points, and if we want to calculate the distance between these data points, we have the attributes, and then we have some distance function that we calculate the distance between these data points, and that's it. So all is regards this function. distance function, similarity function, whatever. And if we want to have a graph, so basically what we have to do is to make distance matrix. Apply this function once for all pairs and store the results in this distance matrix. After that, we can deal it as a graph and operate based on that. Okay, so the only practical issues come from here, that can we afford to store all of this distance matrix? Okay, 5,000 points, why not? 25 something thousands, millions, whatever. 100,000 data points like birds data sets. For some big data, 1 million. 1 million power 2, how much is it? 1 giga, tera. Something. Okay, anyway, try it out. Try the birds data. Calculate the distance matrix for the birds. See if it fits in your memory. So, in principle, we should have enough memory, but in practice, there are so many other things eating the memory in your computer and the distance matrix. So, it's one point. Second is the distance. If we have high dimensional data, okay, birds has just 2 attributes, so maybe we could get away by storing the distance matrix. But if we have, okay, we have this dim data sets, let's say dim 32 or dim 1000. Okay, so then calculating one of this distance, you actually need to calculate the difference between all attributes. If you have 1000 attributes, 1000 steps. And then if you have slow algorithm, okay, k means takes n times k at each step, so yes, okay, whatever 1 million here, and then clusters 100 times what I open, just forget about it, because I'm not so interested. It's anyway usually quite small. But if it's a big like 1000, then you should take it into account. So suddenly your processing time goes up to 1000. Nice. I think Anssi did something about this Python GPU or whatever, this parallelization. How many processors you have there?
On GPU, thousands.
Thousands. Okay. So what if you say that okay, you only have one? Yeah, so it takes time, and now I suddenly say, okay, you have to now spend 1000 more time. Yeah, it nicely runs 5 seconds, and then I say, oh, sorry, now it takes 5000 seconds. So in that case, you might actually be better with the matrix. Calculate it once, store it, and then do it. But yeah, so this is a more like practical consideration. Do you afford the memory, or do you afford the extra computation, recalculating the distances whenever needed? Okay. So, okay, in the literature you may find this kind of graph-based approach. It's the oldest is probably minimum spanning tree. Okay, nice. We have a graph. Aha, we have a huge literature of lots of graph-based methods, graph algorithms. We can calculate minimum spanning trees, whatever graph structures, isolated components, and so on. So yes, okay, we can do it, and then once we have minimum spanning tree, let me see what my slide says, what we should do next. It says nothing. So distance graph, yes, calculate minimum spanning tree, what it takes, or to n power 2 or something like that, depending on the algorithm. Krustal, Prim's algorithm, they are this kind of merge-based methods, and we can get the minimum spanning tree, and there we almost have a clustering, right? Once we have the minimum spanning tree, now we can start to cut. Now we have a kind of original complete graph, then we have a subset of these links, and now we can see, aha, there's a somehow long link here. Let's cut it off. Aha, we have one more cluster. 4 is also quite big link, right? Let's cut it off. Now I have actually 3 clusters already. So nice. So yes. So in principle, this can work, but then in practice, yeah. So practice is a little bit different. I don't know if I have your material about it. Yes. Okay. Okay, but the problem of this single link is that if you have a clusters like that and another cluster here, And we just need one noisy point in between, and then we have a little bit one point. Okay, I would need a good example, but this is kind of this result, this minimum spanning tree, it will result actually the same result as single link algorithm. This is one belongs to the agglomerative clustering, and unfortunately we haven't talked about it yet, but it will find clusters just anyway connecting kind of the nearest neighbors. Doesn't need to have any average connection or average criterion. Okay, but yeah, no. So now this cut, once we have the graph, we can use the same idea that with the minimum spanning tree, cutting the links. So now graph cut is defined so that we cut away certain amount of links to divide the graph into subsets. Yeah, okay, but typically the cost function is to maximize the weight of the edges cut, so cut the biggest edges, and then we could first cut here and the second cut here. So minimum spanning tree is rely only the one link. So if you think, see again at this picture here. So just cutting one link, because MSP has n-1 links, cutting any link. So basically it has only one cluster, everybody is connected, and cutting one link, you kind of make separated components, and these separated components are the clusters. So just cutting one link is enough to create the clusters. But then again, if we have a bad choice with the links, so we are relying too little information. But now we have kind of a little bit too much information, but let's see. We can still do it. If we cut all the links between here, then we are creating two clusters, and the criteria now can be to maximize the weights of these links. Okay, if we have Euclidean space and if we calculate the sum of squared errors, so this actually equals to minimizing the within cluster distances. Because if you remember where these links come from, so if we calculate them just the squared Euclidean distance or take it from there, so they are just the distances. And then all what we cut away, we have a complete graph. What is remaining are the links inside the cluster. So, okay, this is, yeah, I think I better move on. This is not simple to show, but this connection is there, so it's just a different way doing just the same thing. So it's basically is equals to minimizing the mean squared error, or should I say the total squared error. Okay. Then the second approach is that, or the second a little bit or false concept is usually talking about stopping criterion. So these cut-based approaches, they start to cut, and then stop somewhere. But now we already learned that finding the number of clusters, we shouldn't have any stopping criterion, or we shouldn't stop anywhere. So using random swap or some other algorithm, we basically just solve all the possible number of clusters, optimize them separately, or utilize the previous information, whatever, and we get some results, and then we want to find out the minimum according to certain cost function. So the cost function is the critical how to do it. Now we can, of course, do a hierarchical algorithm like agglomerative clustering where we start to merge. So this kind of merge approaches come from here. We have a first very big number of clusters, start to reduce them one by one by merging nearby clusters. And then we are basically doing the same work, calculating all possible clusterings. And the divisive approach is the opposite. We start putting everything into one cluster, start to divide and continue until whatever. So if we use some kind of stopping criterion, simple criterion is that we keep on dividing as long as we get better result as the cost function. And immediately when we start to grow up, we stop. So problem is that then we get stuck into this local minimum, because here we get minimum until here, or decreasing until here. Then next step, adding one more cluster, we actually get worse result. And this really happens, at least in this case in a repeated game is. It also can happen with random swap. So we can't optimize it so closely. The numbers, of course, are not so big difference, but finding the kind of first local minimum just doesn't work. Stopping criterion is not a good idea. Even if we come from the merge approach, it's the same way. We can find out the local minimum. Actually, there are several local minimums everywhere. So it's not even, at least with this, yeah. So that's the divisive approach, that's the agglomerative. So from the cut-based method, so this is so cut is basically the same as partition. Cut-based method, so nothing really content in it, and cut-based algorithm is the same as divisive. So that's why I'm now going to talk the rest of this about this divisive algorithms. I think there's a little bit too much irrelevant stuff here, but let's see about the algorithms then. How to do with this divisive algorithm without graph, without any cutting ideas, just do it algorithmically. So yes, so the good thing about the divisive approach is that it's based on divide and conquer. We want to solve clustering with k clusters, so we start by doing a bigger problem. Yeah, okay. Okay, so the good motivation is that we get a different number of clusters while we are doing it. So in random swap we have to optimize it for each of the k values separately. But here, because we are doing the splitting anyway, so while we are processing finding the k clusters, we get all previous results, k plus 1, k plus 2, and so on. And then if we continue all the way to have only one cluster, most of the working process, when we start with n clusters, then n minus 1 and so on. So most of the work will happen actually here when we have big clusters. Only one cluster divided into two, we have to process lots of points. When we are dividing, when we have already more clusters, we have smaller clusters, and then we decided how to split it, then there are less work to do. So once we reach the k what we want, and if we don't know k, we have to continue to the end anyway, but this tail of the process is actually quite cheap. We have just we have lots of clusters, but they are very small. Deciding which to split and how to split can be solved. Yeah. So the challenges what here are that so everything first in one cluster, so then we don't have to decide what to split. But let's suppose we already split and we have two clusters, so then we have to choose which one to split next. So that's the first question. And second is how to split. Now we decide that okay, this has a, let's say, bigger variance. This kind of heuristic actually works reasonably well. We just have a bigger cluster, there are larger variance than in this cluster, so we decide that to be split. But then how to split? Like that, or maybe like that. So, and then now because of this splitting, yes, if we have some cost function, let the cost function be sum of squared errors, ESC or whatever the. We can of course optimize, make the split, trying to optimize the same function, but then again, making a sequence of locally optimal, this kind of optimal splitting steps, even if we could do it, it doesn't guarantee that we come to the globally optimal result. So wrong order of this, so correct locally optimal splits can end up to suboptimal results. So this is one problem it has. So why the split algorithms, this divisive approach, why it's not as popular as one could imagine, and these are the three reasons really. Okay, I think the first two are really the most. How to do it well? We can of course have always simple criteria. Let's just take the biggest clusters. Let's divide it. Okay, well, take center point, calculate some furthest point, and then divide halfway. Apply maybe k-means with it. So these are not that difficult after all, but okay. So the general idea is a simple repeat until loop. Select the cluster to be split, and then split the clusters. And and that they update any data structures. So when we are computer scientists and when we don't want to do things efficiently, well, then we need some structures, tree structures, heaps, whatever. So k-means we don't need anything. We just have the set of centroids, we have the data points, and all we do is calculate the distances and keep iterating. So that's why it is so popular. Okay, so let's see how to do it. So I think you can pretty much guess already by now that this is going to work better than k-means. No big surprise, right? Why would I teach it otherwise? So then again, we already have random swap, so can I beat random swap? So let's see. And okay, I keep the goal already at this stage that if we just apply the random swap and if we apply the best split, what will come out of here, they will reach about the same level. I can't really say which one is better or which one is worse. But the trick is that if I take the simplest choices here, then random swap will win without the fight. So we really have to make all the correct choices. Okay, first of all, heuristic choices. Select the cluster with highest variance. So how to split? So which cluster to split? Of course, select the biggest, easiest. Okay, and not just the number of points. So if this has 100 clusters, 100 points, this has 50 points. So let's divide that one. But instead, have the total squared error for these two clusters and measure on the base of that. It's good, but it's still just heuristic. It's not the optimal. And there are some, of course, people who start to think about it. Okay, let's divide the cluster. Let's divide the cluster that has subclusters, right? So yes, really nice idea. But then again, how do we know which cluster has subclusters? Because we are doing the clustering here. But now think about it. Yeah, okay, so there are some heuristics like skew distribution. We want to estimate the all pairwise distances or something and see how the distribution looks like. So typically if we take all pairwise distances here, the distance histogram looks like some Gaussian or whatever. But if we have separate clusters, yeah, they might be too big histogram or something. And some statistical measures like third moment might actually be able to capture this kind of pattern, recognize it, and then do it. But yeah, but we don't need that. Instead, I would like to do things. My favorite algorithm in many cases is brute force. So it's not the best choice usually, but here it actually is optimal choice. So if I can choose to divide this or divide that, or if I already have 7 clusters, try them all and then select the best. Why not? If I have lots of computation, I can just divide this and okay, how do I know which is the best? Okay, now remember that the goodness of clustering is just summing up the goodness of clusters. So for each cluster I can calculate, I already know this cluster, what is its variance, because this variance is pretty much same as the sum of squared errors, this TSC or MSC or whatever. This is basically the same quantity. So that I can easily calculate because I have the centroid. I have calculated at some moment the distances to the centroids already. So all I need to do is just to keep them stored somewhere. And then I keep the sum of this cluster, whatever this sums up. So I keep it for this cluster, I keep it for that cluster and so on. So I know these values. So all I need to do is then to split it. Let's suppose I have algorithm X. If I have this cluster, my algorithm chooses to split it like that. Okay, that's maybe not the best choice, but let's do the splitting algorithm, whether how we split. That's the second question. First, we just assume it fix it. So if this our algorithm produces this split, we have now this subcluster, we can calculate this 1A and this TSC 1B. Let's calculate the total squared error of this part and this part, sum it up, and compare what it was before. I claim that this sum is smaller than this one. Do you believe me? if I have one cluster, I have some variance, and if I split it to two and I calculate the variance of these subclusters, the sum of these variances is smaller than the total variance. And this is just because the more clusters I have, the smaller the TSC goes. So adding one more cluster by splitting this is definitely this overall. And if this overall measures for this cluster dividing into, so basically in this subpart I have one cluster and now I'm going to have two clusters. So definitely TSC is going down, even if I have a bad way to split it. I think it's even impossible to make such a split that TSC, this total TSC would actually go up. So that's all I need. I calculate kind of a delta TSC, how much this TSC is changing. And the good thing is that I don't even need to worry about the TSC of these other clusters, or the total TSC of the entire data. All I need to measure it for this single cluster. Okay. But then again, if I want to do it optimally, like here, then I have to do it for all of these clusters. Okay, so that's a little bit work I need to do. But now, so I will do it just tentatively. I don't do it a split. I just do it, pretend to do it, and see how much it improves. And I store at this delta TSC value. And now I know how much the effect would be. And then I select the best. So simple as that. Okay, and the trick comes at here, this third part of this is how much it costs to calculate all of it. Because yeah, lots of extra work, I have to actually do it. Because if you just select the TSC of this cluster and select based on that, it's just kind of a odd to one type. You don't need to calculate anything, but here I actually have to split all of them and then do it. But the trick is that actually all of this extra work just doubles. So if your simple heuristic algorithm spends 20 seconds of doing this entire clustering process, my extra work doubles it, no more. And the trick is that once I do this tentative splitting here, so I do it, I don't throw it away. Well, actually, I can throw it away, but I keep the statistics. So the delta TSC I store it for here. So now let's suppose I have this delta value stored for all of these clusters, and this I find out this is the best to split. And then I split it. Okay, now let's assume we have the better algorithm there, and it actually splits it like that. It doesn't matter because whatever our splitting is. So now we split it. So we have done one split, and now we do to repeat the process. So what do we do next? We need to decide which cluster to split next. So how to do it? Compare all of these delta values of these clusters. Aha, but we already have them. I stored them. This we don't have, and this we don't have. So I need to calculate two more splits. So I need to update this. I need to find out, okay, if I split now this cluster here, how to do it? Okay, let's say the algorithm says here, I get delta value here and here. Then how about if I split with this one? Okay, algorithm says let's split like that. I have one delta here, and that's it. So I need to only do the new calculations only for this cluster. So I need to apply two more splits. Okay. Yeah. I would like to have a little bit of space somewhere, but I'm a little bit lacking of space. So basically you think we start with one cluster, everything is one cluster. We split it, we will have two clusters, then we split this one, we have three clusters, then let's split this one we have here. It's kind of a binary tree. And then somewhere we stop. We have k clusters what we want, and once we have k clusters, then we stop the process. Right. So we have there basically k minus 1 splits in total. But this optimal choice, I need to do the tentative splits, what it means. So if this is my final result, so after, because I don't know when I get it there, so for example, when I split this one, I have these two. So what I need to do is the tentative splits here. I do the tentative splits here also, and then I make the choice. This was split. Then I need to do the tentative splits for this one. Okay, this was split. Okay, this new comes. I need to do the tentative splits for these two, and also this one. So basically I need to go one level further in this tentative splitting than the algorithm really goes. And that's where the 2 times come from. So this is my final tree, I will end up in this binary tree view of this splitting approach. And I have one extra node. And now if you think about binary trees, how many leaf nodes you have? And how many internal nodes? If I have k minus 1 internal nodes, how many leaf nodes the tree has? This is independent of the size of the tree as long as it's binary. So here we have 3 internal nodes. Can you repeat? Yeah, it's 2 times. The total number of nodes is twice as the number of internal nodes, minus 1. So if I have 3 internal nodes, I will have, if I have k internal nodes, I have k plus 1 leaf nodes. So in total I have 2 times k minus 1 number of nodes in total. And the node represents how many splits I have to prepare. And that's where the 2 times come from, because the simple algorithms only need to do the real splits. I need to do 1 level further. And this 1 level further causes double work. Okay, so okay, let's see example. So here's a selection. This is a process of one of the S sets, and you can see these numbers here are now the total variance. Actually, I'm not sure what's the number here. So it's probably that this is the total squared error of that cluster, and this one has the biggest one. But if we divide this one, actually dividing that one, this cluster actually will cause most benefit. And yeah, it's not easy to see from these numbers or anywhere else. Now as this is 2-dimensional data, we can spy the data. We can see that these are 4 clusters and here's 3. Okay, maybe that's the reason or whatever formulation, but dividing that cluster actually benefits more. Of course, in the long run, both has to be split anyway, so not so big deal. But that's how the algorithm goes. It has stored all of these values, yeah. I think this is not the value. We should have the delta TSC stored, not the total TSCs here. But basically this is divided and we have two new values there. So next one is split. Oops, so that was really that short example. Yeah, okay. So let's consider the next question, then how to split. So choosing which one to split is actually quite simple. Try it all and select the best. And only twice extra work, so that was the surprising effect. We can actually afford to do it. If you can afford 5 seconds, you can afford 10 seconds. I just go with answer and buy one more processor or something, right? I don't know, does it work that simple, but in principle. Okay, how to split. So now we have one cluster, and during the process this cluster can be very complicated. There can be real clusters inside it, and now we need to decide how to split. And the centroid was somewhere here. Okay, some old ideas, there was this kind of algorithm in vector quantization called Linde-Busso-Gray, and they used k-means, and for this k-means they initialized by splitting. And their splitting strategy was simply to, binary split, every node was split, so a little bit naive, actually quite naive, and also just simple, take the centroids and move it a little bit plus minus some epsilon. Okay, question is how much is epsilon? And then, okay, which direction is the epsilon? So having this kind of noise vector in multidimensional cases is already not trivial to do, but yeah, we could take the principal axis of whatever, and we could decide that, okay, let's put it here and here. Then we have 2 new centroids. And so the idea, so I thought this is a centroid-based method that we take the original centroid, make a copy or make another one, put the other one there, and then apply partition according to the data, and that's how we split. So optimal partition within the cluster. Okay, then of course, after we realized that one, we also realized that no need to do this kind of simple things. Let's take a better heuristic. Two furthest vectors. Okay, simple strategy would be, okay, first of all, if you have n points here, or n vectors, we have n power 2 pairs. To select the two furthest can be a little bit time consuming to calculate, especially at the early stage where we have all points in one big cluster. We would spend immediately n power 2. So, not that great idea. So, many people use the following trick. Let's take the center. Let's select the furthest from the center. Aha. Now I have only n calculations. Okay, I will find out that yeah, this point is the furthest from center. Then at next step, I select the furthest for that point. Aha, another n calculations. It's here. Found. Of course, if we have bad luck, we may not find the two furthest. But in many cases, we are going to find two vectors that are quite far from each other. So yeah, nice idea. And now we have more likely to make a nice good split. And then, with these vectors, we calculate again the nearest centroid for every point, and we will have some kind of split. Yeah, so I think this is nice idea. And the third one is really lazy. No bother to do any calculation. Let's just take two random somewhere. Let's take one here, another one here. And then let's split like that. Yeah, well, the trick of this approach that is assumes that we are going to apply k-means anyway. So in many variants, this split is actually combined with k-means. And yeah, we can actually because we can apply k-means inside this cluster. So once we have these points, then we can calculate all of the points, which is the nearest. And all of this will be mapped here. Actually, no much changes. But k-means will then update this location, and because they are so popular here in the south, it will actually move there. So I don't know where it moves. It probably moves directly here, and this moves somewhere here. And then this is iterated a couple of times, and this is, in most cases, it will work pretty well. We didn't study that well, and I'm a little bit surprising that in our studies we found this as the worst approach. So I would like to study this again more deeper to find out, is it really that bad, and if they just combine with k-means, is it just good enough? So for me this is a bit question mark, so how good or how bad that is. But yeah, our test really showed that none of them is actually so good. So not really know why, but that comes the reason that we ended up to do some even better approach. Maybe we were so stubborn that we needed to. We have already the good algorithm, the random swap or whatever. Agglomerative clustering also pretty good. This merge-based that I promised this video lecture forever, and hopefully it will come sometime after the course before the Juhannus. But those gave kind of a benchmark that we already have the result of the good algorithm. What is the expectation? And then we have the splitting. Worked reasonably well, yes, actually it was quite nice, but it's still worse in the TSC than these better algorithms. Maybe that was our reason, because this is quite long, 20 years ago already when we did these studies. So we really have this high quality benchmark, so we wanted to do it better. And we find out that this was not good enough if we wanted to compete with the better algorithms. So that's why we came with this idea to do so how to do it better. So yeah, so this is based on principal component or principal axis. Principal axis is pretty much the same as a regression line in our case. And so let's see how it goes. I think it doesn't need to be principal axis as long as we have some axis. So we have to solve what is the axis, and if our cluster is like that, the regression line for this principal axis is pretty much finding the direction of maximum variance. And this direction is most likely containing the best split. And then, okay, after we solving this principal axis, then we select the dividing point at the axis. So now we have this axis, and we have to select dividing point somewhere here. And then once we decide, let's select like the middle center, we can project all of these values into this axis, we can sort them, we can calculate the average, median, whatever criterion. we have transformed the data in one-dimensional way, and we can utilize that information. So then we select the dividing point at this axis. And tada, what we do with this dividing point? We have multidimensional space. We use hyperplane that is, how do you say, in English this is pretty difficult word for me, perpendicular or something, kohtisuoraan. So 90-degree angle between the line and this. And it's in three-dimensional space, you can already see that it's not really line. If we have this 3D space here, and I have principal axis going like that, it will be plane. Right? But anyway, this plane is, I need just this point. This point will uniquely define this plane. Just if it goes like that, it's like that. If it goes like that, then it's kohtisuoraan. Yeah. So that's what we do. So hyperplane is defined just by this dividing point uniquely. And then after that dividing point, we have kind of divided the points into two sides, calculate the centroids of both parts, and that's it. Again, you can apply k-means and whatever. Yeah. So let's see examples. This is if we start with this data set. Principal axis goes here. It's quite obvious, isn't it? No. Well, if the data is really distributed to anywhere, so there's no clearly primary axis or something that is a maximum variance is this way. So it's just pretty much here we could have basically any random axis and apply that one. But once we have the axis and then we find out the point where we divide, then we will have the dividing plane. And that's will divide. Okay, now you can already see that this might not be that good idea after all. The splitting will have some effects. You can see these four clusters that happens to be in both sides of this plane. So something bad will happen eventually, and that's the one reason why this splitting approach, if you want to do it well, you really have to be careful with it. Okay, so pseudocode, how it goes exactly. So yeah, this is the next. So how we select the dividing point. So principal axis, we have to do calculate regression line, and the best I know what to do is principal component analysis. I think we applied so-called power method, because I think this takes to calculate if we have n points, n times if we have d dimensions, I think we have d power 2. We have to calculate covariance matrix of all the attributes, and all data points contribute to that. So this is already pretty involving step, not something trivial to do. So it may take a little bit more time, and if you have high dimensional data, this power method make it roughly linear with the d. So this is can be done. You will find the tools for it, but nothing that I can simply point out a simple algorithm how to do it. But the next step is more interesting in algorithmic point of view, at least. How to find the dividing point? Okay, calculate the average, right? Median, whatever. Why need even to talk about it? Well, you know, it's if I have, this is my clusters. Okay, pretty obvious that should I stop soon? No, I will continue a few seconds more. Okay, principal axis goes like that. Where is the average point? Somewhere here, right? Where's the median? Well, somewhere here also. I don't think that's the best dividing point, right? I should divide it here, not somewhere in the middle. So to find what is the best dividing point actually does matter. And that's why what was my favorite algorithm? Brute force, yes. So let's find the optimal dividing point. Hey, wait a minute, there's lots of dividing points here, is it? Right? How many dividing points can you have? Many. But I actually claim that if I have n points, I have only maximum n dividing points that are unique. Okay, first of all, if I project all of the points into that axis, I will have sorting of the points. Now I can actually guess, and this my dividing plane is actually perpendicular kohti suoraan about this plane. So now if I take, and now I don't select any point, because if I have one point here and next point is here, how many meaningful dividing plane I can have between here? One. It doesn't matter if I divide here or here, it will be the same result anyway. So what I do exactly is that I will select the point itself as a dividing point. First I select that the first point here. So it means that if you are the dividing point, you will belong to the left cluster, all the rest to the right cluster. Then I have the next dividing point here. Okay, I consider that, then you both will belong to the left cluster and the rest to the right. Aha, and now you can see what I'm doing. So I actually move the dividing point, select the first one, and I put one point in the left, rest to the right. And then I move the dividing point one step at a time. And the interesting trick is that this moving this dividing line to the next candidate position, only one point will change the cluster. Okay, if I have the cluster here, I have another cluster here, and one point will change the cluster. I know the square error of this cluster, square error of that cluster. For this change, how much work does it take to recalculate the values? Yes, does it say somewhere here? Yes, it only takes order 1, because I know the central point here, I know the central point here, I know the number of points here, I know the number of points here. So what I'm actually doing, I'm subtracting this away from that cluster. And this difference I can calculate by simple equation. It's actually the difference of the point itself and the centroid weighted by the size of this cluster. So it's kind of dividing this. And then opposite is done here. So here I have something is subtracted, here something is added. Same equation, I have the center point here, I have this point location here. I calculate the distance and then have the size of this. So this will actually move the centroid to that direction by the amount that is affected by the distance and by the weight. So if this is 100 points already and 1 point here, its effect is about 1 divided by 100 roughly. Plus minus 1, don't remember the exact equation, but yeah. So all I need to do, in fact I can start so that I have a 0 points here and the end points here. So this is trivial to do because we already have the TSE here, we have the center of that one, and then moving 1 point one at a time. So I will take n steps here, and at every step takes order 1 time to calculate, so in total this will take order n time. So, surprising. And okay, now I have all possible n dividing points, and then I just choose the one that minimizes the sum of the distortion, the square error of the left cluster and the right cluster. So that's it. Yeah, and this is the equation. This actually comes from the merge-based agglomerative clustering, where we merge two clusters, and it was shown there that the merge cost, how it can be calculated by simply by the distance of the two cluster centers and their weight. Now the difference is that we have only one weight of the one vector, and then we have the n here. And then this is that the difference varies, of course, or the difference to the previous or new, and then the difference to the other, or the distance squared, of course, and then the weight. So the way it's added, the weight is just the size of the cluster by size of the cluster plus 1, and then removed. So here the effect is kind of, something is reduced from the distortion or the error, squared error, and here it's added. So this is the change, what happens, and whatever is the previous, now the total is total plus this change, we get updated. And then updating the centroid is also the same. We just take the weighted average of the previous centroid, adding the new point, weighted by the size of the cluster and divided by the new size. So pretty trivial to calculate and fast. Okay, so far so good. So little bit effort, we can actually do every step. Selecting the cluster to split, we can select the optimal and do the finding the splitting point according to this axis. Okay, still the bottleneck is the axis. What if I make a bad choice of the axis? So this still can't guarantee the optimality, and yes. And there is this kind of, so locally optimal choice may fail to find the globally optimal solution. So now in this case, yeah, the principal axis is pretty much here. Finding the optimal dividing point, yes. You might assume that the optimal dividing point would be here, right? But if you calculate the squared error of this cluster, the center would be here, and the squared distance from here to centroid is pretty big. So actually, the optimal clustering of this data for two clusters, if we have fixed that there must be two clusters, so the optimal dividing point is here. It will be this cluster and that cluster. But then again, we know that the next step is we want three clusters, and this is only intermediate result, and that's the problem of local optimizer. You don't have the vision for the global. So we made a mistake, and then we will suffer for it, because next we have to divide this, so we will end up with these three clusters, or vice versa. Okay, that's at least in theory. So let's see what happens in practice. So this is now one of the S sets. Okay, we have already two clusters. Now we are finding the next. We have a principal axis here. Okay, that's quite obvious that this is the maximum variance. And finding the optimal dividing point is that one. Okay, we divide, and this is the new result here. Dividing is done, and then we do the next best cluster, so it's the bigger one here. Principal axis again quite easy to see. Optimal dividing point is here, and we divide. Now we have four clusters. Next, this will be split, and you can see the splitting line. Result is here. Next will be split this one. 6 clusters now. Next we split the bottom right cluster, 7 clusters, top left. Bottom left there. Again this top left. Splitting continues here in the middle. On the top right, okay, here we still have 3 clusters inside, so that's divided. Then here at the bottom, okay, there I think we divided here this in the center, and here at the bottom, now we have already 14 clusters. Last split, this one. And if we know that there are 15 clusters, this will be the result. So as you can see, it actually does find result that has the correct global allocation of the centroids. There are 0 errors in that sense. Total scored error will be 1.94. And there are a little bit roughness, if you can see. This centroid, for example, it should be a little bit to the left. And you can see the original splitting lines making the problem. So these points there assign it to the wrong cluster. So we have these kind of problems remaining. Now, simple trick is to refine by k-means, because we have it in the back pocket anyway. So let's take it there, apply. Unless it's very costly, you have this kind of ancient calculator, and you apply clustering k-mean calculator, and it takes 1 hour to calculate k-means and only half an hour for the split, and then you maybe don't want to wait. But yeah, so and we don't necessarily need to do the entire k-means. So we have 9.54. We can simply apply repartition. So let's take every point, because they were optimized, then splitting lines were applied, so it's some can be rough. So let's recalculate the new nearest center for every point. And the result already drops down to 1.39. And then if we apply k-means, we can get it even further. So the most drop comes here. We can simply reallocate the points and get the reduction, complete application of k-means, and you can see this is the result. We will find the optimal, well, I don't know if it's the globally optimal exactly, maybe there's a little bit tuning somewhere that could be done better, but we can see that it's pretty much the same. Definitely 0 errors in CI, and I think this is pretty much the same as random swap and genetic algorithm or whatever for this data. So a little bit changes in some clusters, but not so big. So that all we need to do. Yeah, so at this moment I would like to go 20 years back on the history and start the study again, and let's repeat this with the other simpler variants. Can we make the same result with the k-means or not? So this is a little bit open question to me. Okay, so, but let's see how much it costs. Time complexity. Okay, now k-means we know already. You have some idea who has implemented it and tested how much it costs, so it is not that fast. It may take a couple of seconds and we might need it real times. For simple sets like S sets or whatever. Take the birds data sets, I think it can go a couple of minutes, depending on your device and the details. So yeah, we might need something fast, and yes, this is faster. Remember all the steps what we have there. Linear time, this linear time, that k-means have n about n times k, and the number of iterations was something like 25. Then we have n. Let's suppose. Well, okay, let's first consider S sets 5,000 and k is 15. So this kind. So or plus the dd and whatever constants. Okay, so this. Now, this is pretty much every step is linear time. It depends on the size of the cluster we process. And at first, we have everything in one cluster. So we have all possible vectors. So we have to do linear time processing at the first step. After that, we have half size. Okay, this is approximation. We can't know what is the sizes of the resulting clusters, but in most cases, they are half size. So next time we process, we will process the big cluster first, n points, then we have n divided by half points here, and here we divide them. And then we process these 4 clusters, we have n divided by 4 size, and so on. This is just the best case scenario, so in fact it can be worse, but if you look, most of the work comes here. And now a little bit combining of this equation, you can see n plus 2 times n divided by 2, 4 times n divided by 4, and so on. I think the final step, here I have m now is the same as k. So this is the number of clusters. So we have m divided by 2 times n divided by m divided by 2. So 2 basically goes up there. Now then they will eliminate each other. This will eliminate each other. So n is remaining. And all of these steps, 2 are eliminated each other, these are eliminated each other, so it's n plus n plus n plus n, and the question is just how many steps we have there. So this is not the number of steps, but how many terms we have. Well, the number of terms, I think it's a logarithm. I think this is probably should be logarithm of n. Yeah. Okay, there are some further analysis. I will skip this one, but now this assumes that all the times they are equally split into 2 equal sizes and so on. And this analysis, if you took the algorithm course in autumn, we had a very similar exercise there with the linear time selection or something. The question, if the bigger, if we divide into 2 halves, two sublists or whatever, if the smaller one is some proportion of the other one, so we divide, let's say, like 75% and 25%. So any constant proportion we apply this relation, it still will result after this analysis. It will come up to the linear time dependency on here on n. So this p is just a divider. So if we have the smaller one 0.1, then it will be 1 divided by that, it will take 10 times. So yes, it has a constant factor, the increasing factor of the size. So this kind of unbalance will have an effect, but the time complexity still remains pretty much. I think the correct result here, so this was just the size of the cluster, but then, here we actually apply the t here, we get blah blah blah, n log something, and then this is just assuming the linear time, but we actually have a little bit more. We have to sort. So that what was kind of forgotten at this stage. Because once we have the points here, we have to calculate the principal axis. That's basically linear time with the dimensionality. But after we have it, we have to sort them. Because when we find out the optimal dividing point, we have to move it one by one. So n steps, but have to order, we have to sort it. And this sorting takes n times log n. So that we can't avoid. And this is, so instead of summing up n's, we are summing up n log n's. And now the size is here that is changing, whatever. So now in this equation, we assume that the p is there, some constant factor that we divide into, that is p proportion of the full size and the rest. So they are not equal sizes, but whatever this p, this will come up to this equation and end up upper bounded by number. So don't go to the details, but the result will be n log n times log k. So there are actually two logarithms. It's not just simple n log n, almost there, but also multiplied by logarithm of the number of clusters. If it's small, logarithm of 15 is about 4, so it has some multiplier there. Logarithm of 5,000, it's what, 12 point something, and then 5,000 if this is a essay. So you can see 5,000 times 12 times 4, okay, this together 68 or something. It's still much smaller than that, so this n is still dominating factor. So this logarithm will be significantly smaller. So in total, this is much smaller than n power 2. And k means you have n times k. So if you have lots of clusters, n times k is already n power 2. So yes. So in principle, it is faster than k means. So n log n is quite good. Okay, so some practical result. This is oh wow, Birch one set. Okay, this must be done by my students on some years ago. Now, the splitting algorithm. There seems to be two variants, and I unfortunately can't remember which is which, but two different variants. The total squared error here, and time, how much it takes to process. So you can see. Okay, now we have the birds. If you run it yourself, you have some idea how long it takes. So this splitting algorithm here takes, well, it's not still super fast. It still takes some time, but these are old numbers. Today might be already much faster. Something 20 plus seconds, but a little bit high. But remember, applying this k-means. Okay, here we have this splitting and applying k-means. I think it's this number we get already at this level. A little bit takes the time. And two variants that I didn't even mention. These are split with local repartition. It's basically meaning that after we do the split, we apply k-means inside the cluster, allowing to move to the neighboring cluster of this kind. Some local, similar that in the random swap. So when we do some changes, all the vectors are affecting clusters. They are finding new nearest center, so they are allowed to move also away from this splitting cluster. This I don't remember, are they allowed to attract from outside or not, but pretty much same thing as applying k-means, but faster. So from here to here, there's only very little penalty for the time, but we can get to the same level. And then here is really the ultimate variant, where we do the split and then apply k-means immediately. Then do the next split, apply k-means. So do the k-means during the process of the time. So this becomes already much slower, but we can still get even better. Problem of this variant that when we do k-means, we are storing this splitting tentative splits, and we have to update these values, because if you apply k-means, these split values are also going to change. So I don't remember how we solved it. We probably implemented a special update strategy for that one, and for that reason I can't really recommend this to apply the k-means at every step. At least if we do this optimal choice of the which cluster to split. Yeah. So yeah. Now this result actually requires that we have the optimal choice which cluster to split. So that was required, and the second is to do the actually optimal split point, or the dividing point. So both of them were needed. If I sacrifice one of these components, I don't know how much it affects the results. So this isn't shown here. So now different combinations probably can be found. Maybe better dividing line or something. So conclusions. So these devices algorithms, they are efficient and good quality clustering, same as anonymous fab. I don't have extensive comparison. I think I should make it and find out at least for this our favorite datasets to see how it really compares. But several non-trivial design choices. So the actual implementation, I can't show you pseudocode here because it doesn't fit into one page. Okay, I can show series of pseudocodes of every step, but not easy to do. And then selection tree. This is interesting. I would really think, could we have a better access there or better computers overall? So I little bit feel like, yeah. I hope you don't feel like this today now that get all the information in a short time and needs a couple of months to digest what was learned. But I still feel there's something more that could be done, at least theoretically. I'm at least interested to, is this the final truth or is there something to be done, either to make it faster, simpler, or even better result overall. Yeah, and I think I should probably write a new paper about this divisive algorithms, because all of this is pretty much explained in just one paper about 20 years ago already. So almost like nothing has changed ever since. So there must be always something to be improved. And all the other papers, they are pretty much, well, okay, these are discard-based methods, whatever. I don't really think they are worth to study that much, but so let's see what the future will show.